Consider the scale of the global power grid at this exact moment. Every light bulb in every city, every automated factory floor, and every server farm currently processing the internet. Based on current projections for AI growth and transportation, this entire footprint is about to expand. Within the next 25 years, humanity will require nearly 3 times as much energy as we consume today. This image of a solar installation in the desert highlights the physical challenge of meeting that demand. Solar and wind are low-density energy sources, meaning they require an immense geographic footprint to capture a meaningful amount of power. To hit that 300% target by simply building more of what we have now, we would need to cover vast stretches of land in panels and turbines. At a certain point, we simply run out of available space and raw materials. This visualization shows the second-by-second balance required to keep a grid alive. To maintain a stable 60 Hz frequency, supply must perfectly match demand at all times. If that balance tips, the entire system destabilizes, leading to catastrophic failures. This is the primary hurdle for solar and wind. Because they are weather-dependent, they are intermittent. You cannot force the wind to blow or the sun to shine, just because a hospital or a data center needs power at 3 in the morning. These critical institutions require baseload power, an uninterrupted 24/7 bedrock of electricity that remains constant regardless of the weather or geographical luck. Historically, we got that reliability by burning coal or gas. To reach a zero-emission future, we have to find new ways to generate that constant supply, looking beneath the Earth's surface and into the mechanics of the atom. Traditional geothermal energy was a geographic lottery, restricted to rare places like Iceland, where heat naturally rises to the surface. But a new approach is turning that niche resource into a universal option. This schematic of an enhanced geothermal system shows how we can drill thousands of meters straight into the crust. By reaching rock heated to 400 degrees Celsius and creating artificial fractures, we can tap the Earth's internal radiator almost anywhere. Cool fluid is pumped down into those fractures to absorb the heat, then returns to the surface as high-pressure steam. This closed-loop system provides power 24 hours a day. By using engineering to create the permeability that nature didn't provide, we move from a weather-dependent grid to one supported by a scalable, always-on power source. Below the crust, we are also discovering a new primary resource, geologic hydrogen. For decades, we thought we had to manufacture hydrogen in labs, but it turns out the Earth has been producing it naturally through chemical reactions deep underground. This diagram shows the first step in the recovery process. Specialized drones use sensors to identify pockets of pure hydrogen gas trapped under impermeable rock domes, allowing us to locate these deposits with high precision. The center column of this schematic shows the infrastructure needed to bring that gas to the surface. Once extracted, it is managed in large-scale storage tanks, providing a carbon-free fuel source that is as energy-dense as the fossil fuels we are moving away from. Extracting naturally occurring hydrogen is a significant strategic shift. Instead of using massive amounts of electricity to create synthetic fuel, we can simply mine a clean, primary resource that is already there. This pivot toward heavy-hitting power is being championed by private sector leaders like Bill Gates, who are investing in a new generation of atomic energy. While current designs make traditional fission safer, the long-term focus is on nuclear fusion. The rightmost schematic shows the core of a fusion reactor. Instead of splitting atoms, fusion forces light hydrogen atoms to combine, replicating the process that powers the sun and yielding massive electricity from microscopic fuel. To make this work, the fuel must be heated to 100 million degrees. Since no material can hold that heat, the reactor uses invisible magnetic fields to suspend the glowing plasma in a vacuum, preventing it from touching the walls. Because it doesn't depend on location or weather, fusion offers a path to high-capacity generation that can be situated exactly where demand is highest, producing no carbon emissions and minimal waste. By integrating these 3 systems, geothermal, hydrogen, and advanced nuclear, we create a baseload triad. This combination provides the reliable, high-density power needed to bridge the gap toward that 3-fold increase in global demand. This blueprint shows the ultimate requirement for any future grid. It must be affordable, reliable, and clean. These breakthroughs move us past the constraints of surface-level renewables to ensure power is available everywhere, all the time, The most significant consequence of this shift is the build anywhere capability. It completely decouples energy production from specific geographic requirements, like sunny deserts, windy coasts, or fossil fuel reserves. When any nation can generate its own industrial-scale power, regardless of its geography, the traditional monopolies on energy resources lose their leverage. In this future, the ability to become an energy superpower is a matter of engineering, not location.